In August 2012, a machine launched in 1977, running on computing power less powerful than a modern digital watch, became the first human-made object to leave our solar system. Voyager 1 crossed the heliopause, the invisible boundary where the sun's influence ends and true interstellar space begins. Scientists had a confident theory about what that crossing would look like. A sharp increase in cosmic ray particles from outside the solar system. A sudden, dramatic shift in magnetic field direction, as the sun's magnetic influence gave way entirely to the magnetic field of the wider galaxy. The cosmic ray spike happened exactly as predicted. The magnetic field shift did not happen at all, and 13 years later, scientists are still trying to explain why. This is the real story of Voyager 1's interstellar mystery, a genuine, peer-reviewed, still unresolved puzzle in space physics that is far stranger and far more scientifically interesting than anything that needs embellishment to be compelling. Let us start with the spacecraft itself, because the engineering achievement underlying this story is almost as remarkable as the mystery it produced. Voyager 1 launched on September 5th, 1977, riding a once-in-a-176-year planetary alignment of Jupiter, Saturn, Uranus, and Neptune that allowed NASA to use each planet's gravity to slingshot the spacecraft progressively faster and farther than any previous mission. It flew by Jupiter in 1979 and Saturn in 1980, capturing some of the most iconic images in the history of planetary science before being flung onto a one-way trajectory out of the solar system entirely, currently traveling at over 17 kilometers per second relative to the Sun. As of March 2026, Voyager 1 sits at a distance of approximately 172 astronomical units from Earth, more than 25 billion kilometers away, making it the most distant human-made object in existence, and it is projected to reach a full light day of distance from Earth by November 2026. It is powered by 3 radioisotope thermoelectric generators, slowly decaying plutonium-238 sources that have provided steady electrical power for nearly half a century and are only now beginning to require NASA engineers to selectively power down individual instruments to conserve the spacecraft's dwindling energy budget. In December 2011, NASA announced that Voyager 1 had entered a region scientists informally nicknamed Cosmic Purgatory, a stagnation zone where charged particles streaming from the sun slow down and turn inward, where the solar magnetic field strength doubles, and where energetic particles originating from inside the solar system drop by nearly half, while detections of high-energy electrons arriving from outside the solar system increased 100-fold. This was the clear sign that the spacecraft was approaching something significant. Then, on August 25, 2012, the moment came. The solar wind particles that Voyager 1's instruments had been detecting for 35 years dropped abruptly to background noise levels. Cosmic ray detectors confirmed a sharp increase in galactic cosmic rays arriving from outside the solar system. By every measurement, scientists had predicted in advance, Voyager 1 had crossed the heliopause and entered true interstellar space, the first human-made object in history to do so. Here is where the real mystery begins, and it is a mystery grounded entirely in verified, repeatedly confirmed instrument data, not speculation. Based on heliospheric models developed by multiple research teams in the years before the crossing, scientists confidently predicted that the direction of the interstellar magnetic field would be sharply different from the Sun's magnetic field, tilted at a steep angle relative to the east-west orientation that characterized the solar magnetic field inside the heliosphere. The expectation was a dramatic, unmistakable rotation in magnetic field direction the moment Voyager 1 crossed the boundary. When the spacecraft actually crossed, the magnetic field direction showed almost no change at all. Not a gradual shift, not a partial rotation. Essentially the same direction and magnitude on both sides of a boundary that was supposed to mark the transition between two entirely separate magnetic environments. This discrepancy was disorienting enough that it genuinely delayed scientific confirmation that Voyager 1 had crossed the heliopause at all. Several research teams proposed alternative explanations in the years immediately following the crossing. Perhaps the magnetic similarity reflected temporary instabilities in the boundary region, or brief flux transfer events, or some other transient phenomenon that would resolve itself as Voyager continued traveling deeper into interstellar space. That resolution has not happened. Now, well over a decade past the crossing, Voyager 1 has been in the interstellar medium for more than 13 years, traveling well over 16 astronomical units beyond the heliopause boundary. The magnetic field orientation it measures remains nearly constant, ruling out the temporary instability explanations that seemed most plausible in 2013 and 2014. The explanation that has gained the most scientific traction comes from a research team led by Dr. Mark Ofer, building on work with colleague Dr. James Drake, and further developed in studies led by Dr. Nathan Schwadron of the University of New Hampshire. Their model proposes that the interstellar magnetic field does not simply sit static and undisturbed outside the heliopause. Instead, as it approaches the boundary, It drapes and twists around the heliopause itself, bending the way a rubber band bends when stretched around a beach ball. Magneto-hydrodynamic simulations run by Ofer and Drake demonstrated that when an interstellar magnetic field encounters the heliopause, it acquires an east-west twisted component that would not occur if the sun's magnetic field were not present and pressing outward against it. In other words, the sun's magnetic influence may extend physically beyond the boundary that is supposed to mark its end, distorting and reshaping the surrounding interstellar magnetic field for some distance before the true, undisturbed interstellar field finally takes over. There is a second, complementary piece of evidence supporting this explanation, discovered by an entirely separate NASA mission. In 2009, the Interstellar Boundary Explorer, or IBEX, detected a previously unknown ribbon-shaped band of energetic neutral atoms arcing across the sky, a feature that became known as the IBEX ribbon. Scientists believe this ribbon traces the influence of the pristine, undisturbed interstellar magnetic field as it interacts with particles streaming outward from the heliosphere. By triangulating observations from IBEX alongside data from Voyager 1 and other spacecraft, a research team led by the University of New Hampshire found that Voyager 1's locally measured magnetic field direction differs from the true interstellar magnetic north, as independently determined by the IBEX ribbon data, by more than 40 degrees. That 40-degree discrepancy is exactly consistent with the rubber band around a beach ball draping model. Voyager 1 is not measuring some impossible anomaly. It is measuring a real, physically distorted magnetic field in the specific region just outside the heliopause where the sun's magnetic influence is still bending the surrounding interstellar field, even though the spacecraft has technically already crossed into interstellar space by every other measurable criterion. NASA's Voyager project scientist, Dr. Linda Spilker, addressed exactly this unresolved puzzle as recently as January 2026 in comments to the Planetary Society. She confirmed explicitly that the effects of the sun's magnetic field appeared to be persisting for an unexpectedly long time. Voyager 1 crossed the heliopause in 2012, Voyager 2 followed in 2018, and scientists are still watching year after year to determine when this magnetic rotation will finally complete, and Voyager's instruments will register the pristine, undisturbed interstellar field direction that other missions have independently confirmed exists. Spilker raised the genuinely open scientific possibility that the spacecraft may be probing an intermediate transitional region, a zone between the heliopause itself and what could be called true, pristine interstellar space further out, a region whose existence and physical properties were not anticipated by pre-2012 heliospheric models, and which Voyager 1 happens to be the only spacecraft in history positioned to directly sample. NASA has now launched a dedicated successor mission specifically to investigate this region from a different vantage point. The Interstellar Mapping and Acceleration Probe, IMAP, began operations to study the boundary of the heliosphere using remote sensing techniques rather than the in-situ direct sampling that Voyager 1 and 2 are uniquely positioned to provide. Combining IMAP's broader remote view of the heliospheric boundary with Voyager's 2 unique direct sampling vantage points should, over the coming years, finally help resolve exactly how far the sun's magnetic influence actually extends past the heliopause, and what is genuinely happening in the transitional zone Voyager 1 has been traveling through for over a decade. There's an additional dimension to this story that involves Voyager's plasma wave instrument specifically, and it deserves accurate explanation because it has been the subject of significant public misunderstanding. Voyager's plasma wave subsystem, led by the late Dr. Don Gurnett of the University of Iowa, detects oscillations generated when plasma, electrically charged gas, interacts with the surrounding interstellar medium. These plasma wave detections were genuinely one of the key pieces of evidence confirming Voyager 1's heliopause crossing in the first place. And they have continued to provide valuable scientific data about the density and behavior of interstellar plasma ever since. These are real, physically explainable wave phenomena generated by known plasma physics processes, not unexplained signals, not patterns resembling communication, and not evidence of anything beyond the well-understood physics of charged particles interacting with electromagnetic fields in deep space. The genuine scientific value of these plasma wave measurements is that they allow researchers to calculate the density of the interstellar medium directly, providing one of the only direct measurements of that density ever obtained by any spacecraft in history. Voyager 1's power situation is also a real and ongoing part of this story, though a far less mysterious one than dramatic framing might suggest. The plutonium-238 powering its 3 generators decays at a known, predictable rate, and NASA engineers have been selectively and deliberately powering down individual scientific instruments over the past several years, specifically to conserve the spacecraft's diminishing energy budget and extend its operational lifetime as long as physically possible. This is careful, deliberate mission management, not an unexplained anomaly, engineers choosing which instruments to sacrifice to keep others, including the magnetometer, providing the magnetic field data at the center of this entire scientific puzzle, operating for as long as the spacecraft's power supply allows. Voyager 1 also carries the Golden Record, a genuine, carefully curated artifact containing music, spoken greetings in 55 languages, and images representing life on Earth, intended as a message for any future spacefaring civilization that might one day encounter the spacecraft drifting through the galaxy. It remains exactly what it always was, a symbolic, deliberately optimistic gesture of curiosity sent outward into the unknown, with essentially zero realistic probability of ever being encountered by anything, given the staggering scale and emptiness of interstellar space, and the multi-thousand-year timescales involved in Voyager, reaching even the vicinity of another star system. What makes the real story scientifically remarkable is that it requires no embellishment whatsoever. A 46-year-old spacecraft running on technology far less sophisticated than the device in your pocket is still actively returning genuinely puzzling data from a region of space no human instrument had ever sampled before. And that data is forcing working physicists to revise their models of how the sun's magnetic influence interacts with the wider galaxy. The magnetic field anomaly is real. It remains genuinely unresolved after more than 13 years of continuous observation. And the leading scientific explanation, a distorted, draped magnetic boundary region extending beyond the heliopause itself, is itself a stranger and more genuinely fascinating possibility than science fiction tends to imagine. Because it suggests the boundary of our solar system is not a clean line at all, but a complex, physically dynamic transition zone that took humanity's most distant machine to actually discover. Voyager 1 will likely continue transmitting data for only a few more years before its power finally runs out entirely. When it does, it will become a silent traveler once again, carrying its golden record, its scientific legacy, and an unresolved magnetic mystery that the next generation of missions will have to finish solving without it. What gives this story its genuine staying power, scientifically speaking, is the timeline itself. This is not a mystery that was solved quickly and forgotten. Researchers proposed transient temporary explanations within the first year or two after the 2012 crossing, expecting the anomaly to resolve itself as Voyager continued outward. It did not resolve. Year after year, the spacecraft kept reporting the same unexpected magnetic field orientation, forcing increasingly sophisticated models and ruling out one explanation after another. The draping hypothesis from Ofer and Drake, refined further by Schwadron's team using IBEX ribbon data, represents over a decade of accumulated scientific work responding to data that simply refused to behave the way anyone expected it to in 2012. This is also a genuinely rare situation in physics, where a single spacecraft has occupied a completely unique vantage point for over a decade, with no second source of comparable data to cross-check against directly. Voyager 2, which crossed the heliopause in a different location in 2018, provides a partial second data point, but the two spacecraft crossed at different times, different locations, and under different solar activity conditions, meaning their data cannot simply be averaged together to resolve the puzzle. This is precisely why NASA's newer IMAP mission matters so much going forward. It offers an entirely independent method of probing the same boundary region from a different scientific angle, using remote sensing of energetic neutral atoms rather than the direct in situ particle and field measurements that only Voyager 1 and 2 have ever been able to provide firsthand. The deeper lesson embedded in this story is one familiar to anyone who has followed major space exploration milestones. Nature consistently turns out to be more intricate than our pre-mission models predict, and the most valuable scientific discoveries often come precisely from the data that fails to match expectations rather than the data that confirms them. Scientists expected a clean, sharp boundary in 2012. What they got instead was evidence of a complex, dynamic transition zone that may extend the sun's influence further into the galaxy than any model anticipated before Voyager 1 actually went there and measured it directly. That is not a disappointing outcome for a 46-year-old spacecraft built with 1970s technology. It is exactly the kind of genuine scientific surprise that justifies sending machines to places no one has ever been, and trusting them to send back the truth even when the truth contradicts what we expected to hear.